My name is Shailen Tuli. I am a developer programs engineer at Google, and I will be talking to you about writing battery-efficient Android apps that use location. So, location-based apps are absolutely everywhere. Transportation apps, geo apps, navigation apps, fitness apps, weather apps, even dating apps all use location. And yet, we have this sad spectacle that all too often users simply turn off location on their devices, which means a lot of these apps either don't work at all or they work in a degraded manner. And why do users do this? Because fairly or not, they associate location with battery drain, and they think turning off location is going to help preserve battery. So this is bad for developers who write all these great apps. It's bad for Android as an ecosystem. And of course, it's terrible for users. So location is used a lot. We know that. And the location APIs currently allow application developers to request location at virtually any time and make pretty aggressive location requests with no barriers. And when your app is in the foreground, when you have an activity that you can see, and it's going to be only a short time, it kind of doesn't matter too much what you're doing. But when you go off in the background, well, that's another story completely. Background location has been identified by us as a major contributor to battery drain and power issues. And aggressive use of background location is a major reason why people disable location on their devices. So, in a response to this, and this has been a persistent problem for many years now, in a response to this, the Android team, starting with Android O, put in place some fairly substantial limits on the gathering of background location. Basically, the sort of TLDR is that apps that are running on O devices have background location gathering throttled. So it's basically location is made available a few times an hour, and that's it. And this applies to everything running on O devices, regardless of the target SDK version. And towards the end of the talk, I'll try to get into sort of the nitty-gritties of what this really means. But for now, that's basically it. You just cannot go crazy in the background and do whatever you want. There are some limits in place. Now, what about pre-O? The majority of devices that are out there in the world are running Android N or lower. What about those devices? And for the foreseeable future, that is going to be the case. This talk is fundamentally about identifying best practices that you can use now in your Android apps when you use location, so that you're writing your apps in a battery-efficient manner. All right, so let's dive into this. I'm going to start off this exploration by talking about location APIs. After that, we'll talk a little bit about sort of what is the exact relationship between location and battery drain, battery loss. And then I'll sort of dive into common use cases that every developer has to address when they're writing location apps, and see if we can come up with some best practices that you can all use in your apps. And we'll sort of end with a discussion of the limits that have been put in Android O, and we'll get into some details on that. Okay, so for historical reasons, there are two ways in which you can get location when using Android apps. There's framework location, and there is fused location. So framework location is the older one. It's been there since the beginning, and it's basically Android.location.location manager, and that gives you kind of a wide API surface whereby you, as app developers, can decide, hey, I want to use GPS, I want to use Wi-Fi, I want to use L, I want to use some sensor, and you can essentially get location as you see fit. This type of location is not optimized for battery, and we discourage you to using this. What we would like you to use instead is fused location provider. So this is available through GMS Core. So instead of Android.location, you have Android.gms.location. And fused location provider provides actually a much narrower API surface, and it sits on top of platform components and hardware components. And the way this works is you tell Fuse location provider what kind of location you want. Coarse location, fine location, how frequently you want it, et cetera, and it sort of just figures out what underlying technologies to use, and how to do this in the most battery efficient way. This location provider is highly optimized for battery, and we would like you to use this. So, what is Fuse location? So there's a bunch of inputs that go into Fuse location. I'll take a couple of minutes and talk about those. There's GPS, Wi-Fi, cell, accelerometer, gyroscope, magnetometer, and a host of others, but these are the big ones. And I want to talk about a few of these purely in terms of what they mean for battery usage. So start with GPS. GPS works great outside. It has some trouble with cities, with tall buildings, but in clear skies, it works fantastically. Super accurate location. It's also really, really terrible for battery. So that's your trade-off. Fantastic location, great accuracy, and really bad for battery. Then you've got Wi-Fi. And the coverage for Wi-Fi, as you can imagine, is mostly indoors. The accuracy is pretty good. You can tell using just Wi-Fi where a person is in a building and what floor they're on. And the power consumption is not as bad as it is for GPS, but Wi-Fi scans are still fairly expensive. So it's not free, it does cost something. And then there's cell. Of course, this is available indoors and outdoors. It's available almost everywhere. The accuracy, unfortunately, with cell is not so great. You're not going to get a location which is accurate to within a few feet. You're going to get location which is accurate to sort of a neighborhood level or a city block, etc. But it's great for power consumption. It basically uses very, very little power, so it's fantastic for that. And then you have these sensors, which play an extremely important role in making Fuse location provider do the right thing, and do the right thing for battery. So you have accelerometer, which measures changes in velocity and changes in position. You have the gyroscope, which measures changes in orientation of your device. And you have the magnetometer, which allows your device to be used as a compass. And this kind of varies a little bit by hardware, but by and large, most of these sensors have very, very little battery cost. And Fuse location provider will use these sensors in conjunction with GPS, Wi-Fi, etc., to give you really, really good location as best as it can with very minimal battery usage. So for instance, if you were to request find location, location that is accurate to within a few feet, a few meters, you would use, Fuse location would use GPS and Wi-Fi. But GPS and Wi-Fi, while they work very well, work much better when you combine them with sensors. So for instance, I mentioned GPS is a little bit jumpy when you are in environments with tall buildings. So imagine Hong Kong, Mumbai, New York City, where I live, San Francisco. Those are challenging environments for GPS. So when GPS gets a little flaky, Fuse location, instead of making expensive GPS scans, will say, oh, let me see what the sensor data tells me. What is the accelerometer telling me about what the device is doing? And it sort of pieces together a pretty good sense of what it is that's happening. Same with Wi-Fi. Wi-Fi can be a bit jumpy. When it gets jumpy, Fuse location provider will not do excessive Wi-Fi scans. Instead, it will start looking at the sensor data and try to get a good sense of what the device might be doing. Indoor maps sort of work like that. There was a time when Google Maps would give you, if you went to a shopping mall, it would say, hey, you're in this shopping mall. Now it's much better. Now it says, you're in this shopping mall, and you're right here in this shopping mall on the 3rd floor. Right? It'll do things like that. And a lot of that is driven by sensors. I mean, if location had to be polled constantly, if the Wi-Fi scans had to be constantly done, that would be terrible for battery. But it doesn't have to do that, because once it gets a Wi-Fi fix, it can then look at the sensor data and figure out in a battery efficient way what to do and where you are you turning, are you moving, etc. So that's basically what it is. So the summary of this is, where possible, given a choice between framework location and Fuse location, you should always use Fuse location. This is our recommendation. Switching to Fuse location, if you're currently using framework location in your apps, is probably the single best thing you can do in terms of battery performance of your apps when it comes to location. So please do this. Okay, so that's where APIs are in terms of location gathering. There's one higher level API that is exposed, that's a Geofencing API, and that should be sort of an important tool for anyone building location apps. So what is geofencing? Geofencing is a case where you can take, you can define a circular region somewhere, and you can say, hey, whenever the device either enters this region or leaves this region or sits in this region for a certain number of hours, do something, let me know. And that's basically how geofencing works. Geofencing is built on top of Fuse location, and it is highly optimized for battery. So basically the way it works is the API, it monitors device proximity to a geofence. The closer you are to the geofence, the more expensive it is. And it basically figures out what is your speed, are you in a car, are you walking, how far are you from the geofence, and it sort of optimizes for battery in terms of monitoring the geofence in the background. We'll talk more about geofencing later on. All right, so we've talked a little bit about APIs, and I've given you a little introduction to Fuse location provider. Now I'm going to talk about sort of what is the relationship between battery drain and location in sort of a concrete way. I mentioned that with Fuse location provider, you have to essentially just tell Fuse location provider what you want. You make a location request, and it sort of does the right thing, and it does the right thing in a battery efficient way. So essentially, what this section is going to be in my talk is going to be about what is a good location request. How do you tell Fuse location provider what it should do? So I would say battery can be measured on 3 points. The discussion can be anchored on these 3 points: accuracy, frequency, and latency. And I'll talk about all of these in quite a lot of detail. So accuracy is, of course, how accurate is your location? How fine do you want it to be? And so the way this works is that you can take the location request object that you create and define a priority. And there's a bunch of priorities that you can choose from, and depending on what you choose, Fuse location will use different technologies under the hood and give you what you want. So the most accurate, the state of the art is priority high accuracy. So this will use GPS if it's available, and every time there is a trade-off between accuracy and battery, battery will lose and accuracy will win. It's going to give you the most accurate location it knows how to do. This is a good kind of a use case for foreground. When you have short-lived activity that's in the foreground or something, this is a terrible idea for background because it's going to be very prohibitively expensive in terms of battery. Related to that is another option, which is priority balanced power accuracy. This will very rarely use GPS when it has GPS batching, but mostly it will not, and it will rely on Wi-Fi. So it's somewhat less accurate, but it's actually much better in terms of battery. And I would recommend for you, if you're writing location apps, consider this as something of a default. It does give you pretty good location without burning out your battery. The next level down is priority low power. And this is going to be hitting cell network. It's not going to be using a lot of Wi-Fi. It will not use GPS. And this will give you coarse location. So you're going to not be able to say, oh, I'm a few feet here, I'm a few feet there, but you will be able to say, I am in this part of Bangalore versus that part of Bangalore. So depending on your use case, this may be all you need, in which case you should never request more expensive location updates than this. And the most interesting of all is the priority no power, which is saying, give me location updates, but do not spend any power. So how does this bit of magic work? In this case, what you're saying to Fuse location provider is, don't calculate any location for me. But if another app running on this device is computing location, let me know those results. So that's what priority no power means. And it's actually an incredibly good tool to have if you're writing location apps, because it doesn't cost your app anything. So that's where accuracy is. OK, let's talk about frequency now. Again, it's fairly simple to understand what this means. The more frequent your updates, your location consumption, the more expensive it is for battery. But it's actually kind of a little bit more than that. So frequency is defined by a method called set interval. And whatever value you pass to set interval, location services is going to try to honor that value. If you say, give me location updates every 2 minutes, it's going to try to do that. If you say, give me updates every 15 seconds, it will try to do that. Generally speaking, apps should pass the largest possible value when using set interval, especially background apps. Using intervals of a few seconds, 15 seconds, 30 seconds, is really something you should reserve for foreground use cases. Location services will sort of just do what you ask it to do. It's up to you to choose wisely. Now, if you say location updates a set interval for 2 minutes, there is a little sort of a caveat there, which is that's just a suggestion. Your location updates may be a little slower or a little faster. And the way they can happen a little faster is if another app is requesting location at a faster rate, that will be brought to your app as well, because this location data is shared between apps. So for that reason, we have another method that we could call when building our location requests, which is set fastest interval. So what you're saying is, set interval says, give me location this many seconds or minutes. Set fastest interval says, give me location, even if it's coming from another app, no faster than what I'm specifying here. So here's a little example. So you create a location request object, and you set its interval to be 5 minutes. So at this point, every 5 minutes, your app is going to have location computed for it. But if you also set a fastest interval, which is in this case 1 minute, any app running out there that is requesting location also, that location will be made available to you, but no faster than 1 minute. This is a pretty good way of not burning the battery yourself. You're relying on other applications to do the work, and you get the location kind of for free that they are doing. It's a passive way of getting location, and it's a pretty powerful way of conserving battery. All right, so that's frequency. So latency is really about when location services has location to give you, how quickly do you need it? How quickly do you want location updates to be given to you? So remember we talked about set interval. When you set interval of 30 seconds or 2 minutes, that's what location services is going to try to use as the interval at which it gives you location. But there is also a method called set max wait time, which is a way of having your location delivered in batches after a few times that it's been computed. So let's go back. Set interval is about how often is location computed for you. Set max wait time is how often location is delivered to you. So let me make this concrete with an example. Again, we create a location request, and we set the interval to 5 minutes. What this means is location is going to be computed for you every 5 minutes. And if in that time, when location is found, when a new location is found, and your app will be woken up, and that location will be given to your app. But if you set a max wait time of 1 hour, which is what I've done here, something different will happen. Your location will still be computed every 5 minutes, but it will be delivered to you in a batch every hour. And you will get 12 location data points, at least in theory. So what this means is instead of being woken up every 5 minutes, your app's going to be woken up every hour, which is dramatically better for location consumption, for battery consumption. So batching is a really, really, really good thing to use, especially for background cases where you don't want your device to get woken up a lot. OK, and if you're using geofencing, the equivalent is set notification responsiveness. Geofencing scans happen every now and then. If you don't need your geofencing to be immediate, you can maybe have a little window to hold off before a geofencing result is given to your app. You can set the responsiveness period to something high, and that is also a very good thing for battery. So here's a classic case of how you build a geofence. You set a circular region, you set when it expires, you set what kind of transitions you want, and you build it. But if to that you add a set notification responsiveness and give it a sufficiently large value, that's going to make your geofencing all the more battery efficient. So that's a bunch of stuff. To summarize, it's a fairly obvious. The more frequent, the more accurate your updates, and the lower your latency, the more expensive it is for battery. So in foreground use cases, you can have it all. You can be frequent, you can be as accurate as you want, you can have as low latency as you want, but for everything else, you're going to have to trade off on one of these or more than one of these. And that's where you get to preserve battery. Okay, so that's a lot of looking at APIs, looking at API calls. You're probably wondering, okay, I have practical problems to solve. What's the best way to solve them? So let's start with an obvious one. You want to know the location of a device. For example, you're a weather app. You want to show the right weather. You need to know where the phone is. So here, I would say, you don't get location updates. You use cached location. Because every time location is obtained for your device, it is cached somewhere. And you can simply request that by using a get last location method. And this will pretty much give you what you need in a lot of cases. And the API also exposes ways of knowing how stale this is or how fresh it is. So if this is not null and it doesn't look too stale to you, use it. You don't need to request location updates at all. You save a ton of battery that way. All right, another use case. You have user-visible foreground updates. For example, a mapping app of some kind. So here, because it is foreground, it's OK to use high accuracy, high frequency, and low latency. It's expensive, but it's OK, because in the foreground, this is pretty much tied to your activity's life cycle, and it will end soon. So typically, what you would do it in an activity, you would, inside the onStart, you would request location updates. But you would also must do the following, which is that in onStop, you remove those location updates. If you don't remove those location updates, location gathering will keep happening long after your activity is there, which is obviously a very, very bad thing to do. OK, another use case. You want to start location updates at a specific location. You want to start location updates when you're near home, when you're near work, near a cricket stadium, whatever. So here, it's a pretty good case of mixing geofencing and location updates. So typically, what will happen is, imagine you have defined a geofence around some area of interest. If a user enters or exits a geofence, location services will let you know. And at that point, you can say, this is the trigger I was waiting for. I'm going to now request location updates. A common pattern for this is the geofence gets triggered, you get notified, you maybe show the user a notification, the user taps on the notification, your app opens up to some activity, and at that point, location updates begin. Something like that. Another common use case where you want location updates, but you only want them tied to a specific user activity. Maybe when the user is riding a bike or driving in a car. So here, we would use the activity recognition API, and we would then have combine that with location updates. It would sort of work like the previous example. Let's say you were tracking bicycling. Location services would tell you when the user is likely to be on a bicycle, and you can take that and then start location updates through the same mechanism I talked about. Start a notification, user taps on a notification, something comes into the foreground, and boom, off you go, location updates. So things can get fairly complex. You may be satisfied with these sort of simple scenarios I have mentioned, but what if you want geofencing and you want activity recognition, all of them to happen at the same time, and then sort of somehow combine that with location updates? We realize that there are complex use cases. So for that reason, we have an exposed an awareness API. And this is a very powerful way. So it basically senses and infers your context. And it manages system health for you, and it does so in a battery-efficient manner. If you're dealing with complex scenarios, awareness API may be exactly what you're looking for. So it tracks lots of things. What time of day is it? What is the location of the device? What are the places nearby? Are there coffee shops nearby? Are there stadiums nearby? Houses of worship? What is the activity of the device? Is a person on a bike? Is it a person on a car? Are there beacons nearby? Is a person wearing headphones? What's the weather like? And what you can do is take all of these contexts and treat sort of a much larger sense of a fence. Basically, you can easily react to changes in multiple aspects of a user's context. And this generalizes the idea of a fence well beyond conventional geofences, which of course are just for location. So here's an example. So you create a context fence, and it tracks three things. You create an activity fence which says, track that the user is driving. It creates a location fence and says, track that this geofence, maybe a stadium geofence or something like that, is being tracked. And then a time geofence, make sure it's this time, between this time and this time. When all of these things are true, your app is, let's say, even in the background, location services will say, all the conditions you specified are true, I'm letting you know you can now do whatever, and that whatever could include location updates. Similarly, there is a snapshot API that is made possible through awareness. And again, it's a simple way to ask for multiple aspects of a user's context. Again, an example. You find out what the current place is. You find out what the current activity is. If the current place is a shopping mall and the activity is walking, hey, maybe it's time for you to start location updates so that you can tell the user as the user walks what stores are nearby, or maybe some discounts that you can offer, et cetera, et cetera, et cetera. The thing is, you're using multiple inputs and multiple contexts, and that can get pretty expensive for battery because you're going to be running a lot of different things. If you use Awareness API, you can minimize the battery costs because Awareness APIs are actually pretty battery optimized. All right, one more use case that I want to spend at least a couple of minutes on, which is long-running background updates tied to specific locations. You want to find all the Starbucks in Bangalore. You want to find all the ATMs, all the metro stops in every metropolitan area. So here we get into a solution that involves dynamic geofences. Location services makes a requirement that you can only use 100 geofences at one time. There are, of course, many more ATMs, many more Starbucks than just 100. And also, maintaining 100 geofences is actually pretty expensive. That's a lot of scanning that location services will have to do, and that's going to drain your battery. So the solution is dynamic geofences. Maybe put a geofence around some city, and when that person enters, when the device enters that city, dynamically register geofences in locations inside that city. So you have the outer geofences, dynamically you put inner geofences. If the person leaves the city, you can remove those dynamic inner geofences that are inside because you don't need them anymore. And this is a way you can actually, in a very battery efficient way, get a lot of geofences, get around the 100 geofence limit, and actually do really pretty amazing things. And now, the problematic one. You want long-running background updates with no visible app component. So basically, think of an app that passively tracks your location for hours or days at a time. So this is a case that keeps people up. This is a case that is inherently problematic. And this is a case where you get into that problem that I initially referred to, that background location gathering is a really, really major drain on battery. But if you have to do it, how do you do it? So let's talk about that. You could run a long-running service of some kind and then request location updates every now and then. The problem with that is, if you plan to run your app on an O device, you can't have these kind of long-running services in the background anymore. So this isn't really anymore a good option for you. The API exposes a method for getting location updates using a pending intent, and that's exactly what you should do. So you request location updates, you give it a location request, you give it a pending intent, And GMS core location services will wake up your app when an update is found. So in cases like this, what should the location request look like? Like, what are you going to do in the background that doesn't burn battery? So you use moderate accuracy, low frequency, and high latency. Let's just look at 3 of those things right now. You do not want accuracy, which is priority high accuracy for any background use cases. This is bad for battery. For frequency, I think a good pattern would be to request updates a few times an hour. Let's say every 15 minutes, which is what I have in this slide. And certainly, you should try to get more updates through passive location gathering. So that's why it's a good idea to set fastest interval to some small amount. This way, if other apps are gathering location, you get that location for free. It doesn't cost you anything. And latency, this is really, really, really important. Again, imagine that you set your interval to 15 minutes. Sorry, imagine if you set your interval for 15 minutes. If you set the max wait time to 1 hour, you will get location updates every hour, but you'll get 4 updates which are calculated every 15 minutes at a time. That's pretty good for background, and that will save battery too. And finally, a very important use case that I'm sure all of you have dealt with, what if you want frequent updates while a user interacts with other apps? So imagine a fitness app or a navigation app. So in this kind of a case, you should use a foreground service. This is sort of the recommendation that we're coming up with, because we believe that when potentially expensive work is being done on behalf of the user, that user should be aware of the work. A foreground service, as you know, requires a persistent notification. The user will be able to see, stuff is being done for me, I like it, I approve of this, or they'll say, I don't like it, and they'll get rid of that. But either way, the user is not having their battery burned in some silent, sinister manner. Okay, so I'm slightly over time, and I'm going to quickly go over location limits. You can see that these location limits are kind of a logical extension of many of the best practices that we've talked about in this talk so far. So I think starting with O, the location story in Android gets fantastic. And it gets fantastic because we throttle background location in a sensible way. And this happens on any app that's running on an O device. So the short of this is the background apps can receive location several times an hour, and that's it. Your location request may be something much more ambitious than that, but you're not going to get that. You're going to get several times an hour. And this happens regardless of target SDK version. You can do batching, but again, you will only get location several times an hour, not much more frequently than that. Also, Wi-Fi scans are much more efficient in O. We figured that people spend a lot of time at home, 6, 8, 10, 12, 15 hours at a time, and a lot of time at work, 6, 8, 10, hopefully not much more than that. But either way, you are inside a place, you're connected to a Wi-Fi access point, and you're not moving. So in Android O, scanning for Wi-Fi is much more efficient. There's also much smarter geofencing in O. So until O, in N and lower, scans for geofencing default to every few seconds. In Android O, it happens every couple of minutes. And we found that in a lot of devices, that can give us 10x savings in terms of battery. So that's really great. Pre-O devices, where there are no limits, location is a very busy thing, even on a device that's actually in the background not being used. In O, with these location limits in place, things are much more serene, things are much more organized, and your battery consumption is much, much less. I'm out of time. I've actually gone over by 3 or 4 minutes. But I would say, I hope you write location apps. I hope you write location apps that are ambitious. And I hope you take away from this talk that it's possible to do that and not sacrifice battery. Go ahead, code it up. Thank you.